Good morning. Thank you very much to the organisers for inviting me. I feel honoured and in a special sort of way honoured because I'm not really an AI expert, but I hope that I can provide at least some perspective on the impact that AI is having on mathematics and on potential future needs of mathematics, how I hope things will develop and how I hope they will not develop. So I'd like to start by just sketching out how things have been for the last, well, roughly since ChatGPT first appeared. That's why I date it back to 2023. So I think the whole history, the recent history of AI and mathematics, or particularly LLMs and mathematics, because AI and mathematics goes back a bit earlier, is one where mathematicians have looked at what LLMs can currently do, felt sort of reassured that they can do this, but they can't do that. And then a few months later, they can do that. So you then have to adjust what you thought and say, okay, they can do that, but they can't do this. And then a year later, it's sort of like this. So in 2023, there were LLMs that were solving problems at a high school level, which was already sort of quite impressive. But there were a lot of vulnerabilities. If you slightly changed the question, you could get a nonsensical answer, and there were sort of questions that, still pretty easy questions that they couldn't solve. And of course, they were hallucinating all the time and confidently giving you wrong answers. And so I think we didn't feel at all threatened by that in the mathematical community. We just thought they can do that, but they're never going to be able to have sort of a properly interesting idea. People's faith in that was considerably shaken in 2024, in the summer in June 2024, when Google DeepMind combined their alpha proof system and their alpha geometry system and tackled the 2024 International Mathematical Olympiad. And the headline said that Google got that alpha proof and alpha geometry got a silver medal. It was slightly more complicated than that because they ran their systems for each problem. It took them sort of up to 3 days to get a solution. But nevertheless, this was definitely a step beyond what we'd seen before. That actually, because to solve a maths Olympiad problem, you really do have to have a genuine mathematical idea. So you couldn't just say this was pure statistical completion of sort of token completion and so on. This was it was really something a little different, and the method was a bit different. It wasn't just giving it to an LLM. So that was another way we could comfort ourselves. Google was using a huge amount of resources, a lot of reinforcement learning and so on, and specialized training towards this one task. And even then, the amount of processing that was needed to solve the problems was vastly greater than the amount of processing that a human mathematician would need. But fast forward another year, and suddenly just the best LLMs were doing it were getting gold medal level at the International Mathematical Olympiad with sort of clever prompting, things like getting one model to propose solutions and another one to criticize them and things like that. And by these sorts of clever interactive methods with using conventional LLMs and working with natural language. Something I didn't mention was that for the 2024 Maths Olympiad, humans had to translate the problems into the proof assistant Lean, and then the proofs that were given were formally checked in Lean. In 2025, everything happened in natural language, so the questions were given to the LLMs in natural language, and the solutions were in natural language, but they were then checked by human markers, the same people who marked the human contestants' work and judged to get a gold medal. And several systems got gold medals, and they got it within the time frame that a human mathematician was given to solve the problem, so it was much faster than the year before. So suddenly things started to seem, if you can start to solve a maths Olympiad problem in a reasonable length of time, then it's not clear that there's some genuine barrier stopping you getting further. And other things started happening by the end of last year. First of all, just reliability in general was greatly improved. All through the year, actually, one of the things, mathematicians started using LLMs for literature search because previously, if you had a mathematical idea but you just didn't know what the right name for that idea was, it was almost impossible to, or it was pretty difficult to find it online. But with an LLM, they can just search the literature and search for ideas and not just search for keywords. So we have a much better search engine thanks to LLMs. And so for that reason, LLMs started to become genuinely helpful in mathematical research. But by this year, it was actually more than just for literature search. So people would say, okay, they're very good at literature search, but they can't actually really have sort of useful ideas. But now, even that's not true. And I would say that my assessment now is that if I'm thinking about a problem, then typically when you're thinking about a problem, you start with the main problem, and then you generate some subsidiary questions. And often those subsidiary questions you feel, I mean, the whole point of generating them is that you hope that they will be both easier than the original problem, but useful to answer. Questions that, if you can answer them, will help you with the original problem. So now it's actually very tempting to, when you generate one of these potentially easier questions, just to feed it to an LLM and see whether the LLM can answer it for you. And I've found in practice that it often can. It does indeed turn out to be something that probably for me would have taken an afternoon's work, but for an LLM, I'm talking in particular about actually OpenAI's Pro models. Perhaps I shouldn't admit that since that's not an open source model, but I happen to have access to it. But I'm sure other models would work as well. And yeah, so I've found that I've been getting, within 15 or 20 minutes, I've been getting answers to these questions without my having to do anything that would have taken potentially sort of 3 hours work without the LLM. And now they're starting to solve research problems. So you may have read, I don't know, it depends how much you follow what's going on in mathematics, but there's been a lot of talk about, there's a collection of problems due to the very famous mathematician Paul Erdős. So somebody who used to be a postdoc of mine, actually, called Thomas Bloom, created a website with all Erdős's unsolved problems, over 1,000 of them, and numbered them. And then suddenly people thought, okay, well, let's see if we can get LLMs to solve open Erdős problems. And they started doing that. And again, initially one could dismiss what they did by saying, oh yes, in some cases the solutions they found were just already there in the literature, and Thomas Bloom hadn't realized that they were answered. So that's not a genuine solution. Sometimes they've been a little bit more than that. They've taken one fairly standard idea and put it together with something else and shown that the problem was, in retrospect, easier than was realized, and probably people hadn't tried too hard to solve the problem. But little by little, the sort of level of what they've been doing has been going up. And I've recently had an experience. It wasn't an Erdős problem, but I put in a problem that was asked in a recent preprint on Archive. And within a couple of hours, I got a solution to that question, which it was a solution that modified in a non-trivial way an existing paper of a young mathematician who's a student actually at MIT called Isaac Rajagopal. I sent it to him, said, does this look correct to you? Because one always has to be a little bit careful. And he looked at it and was pretty sure it was correct. And this was a problem that I would say was at the level of, if you wrote it up, you would have a chapter in a solid chapter in a reasonably good PhD thesis. So I think we've now got just a standard LLM, not purpose-built for this purpose, that is doing mathematics at the level of a quite good PhD student. Now, if we fast forward a little bit, I'm going to jump to the next slide. This is what it feels like to be a mathematician at the moment. So we're sort of working, but the level of what the LLMs can do is rising all the time. So we've got to keep ahead of that. I think it's already difficult if you're starting out as a PhD student in mathematics. It will be very difficult to keep ahead of what LLMs can do. Of course, there is one extra feature, which is that as a beginning PhD student, you can use an LLM. So the real question now is a sort of beginning human mathematician plus LLM able to do things that an LLM can't do on its own. And I don't think we really know the answer. This is a very, very new situation. I mean, what I'm describing now of LLMs doing PhD level mathematics, this is sort of in the last 2 or 3 months that I think we've reached that sort of capability. But I don't need to spell out, the consequences that could happen if this development just continues. If we can just extrapolate the way things have been going for the last, we're already sort of in such a different position from where we were a year ago, and if we're in a similarly different position in a year's time, I just don't really know what the consequences are going to be. I'm quite honest about that. That's all I. Now, the main theme of my talk is that even from the point of view of what you want to get out of a mathematical solution, things aren't totally ideal. If you just ask an LLM a question, it'll give you the answer, and the answer may be correct, but often when you're talking to a human mathematician, what you want is not just the answer, and this is not just true at research level, it's also true when you're learning mathematics. Just to be told the answer to a problem is not the best way of learning mathematics. What you want is, you want some sort of productive struggle. That's always very important when learning. But sometimes you struggle and you're just completely stuck. When you're completely stuck, what do you want? You don't want someone to say, this is the answer. Even then, you want somebody to give you just that little hint that gets you unstuck, and then you can continue thinking, and you can continue this sort of productive struggle. LLMs don't really work like that. They like to tell you the answer. And if you try to interrogate how they came up with the answer, it's quite difficult to get a good response from that point of view. So, of course, they have chains of thought, and you can look at those, you can read them, but you're never quite sure whether that chain of thought is really what was actually going on inside the LLM, and maybe there's a lot of dead ends that the LLM explored and just didn't tell you about in its chain of thought. And also the chain of thought, often in research level problems, or such as the ones I've been talking about, what you see is, I'm trying this, maybe we could expand this, and then it just gets to the end of a paragraph and then says, I'm trying this. It just jumps to something completely different. It doesn't tell you why it abandoned the first thing that it was trying. It just jumps to something else. So it sort of jumps about, and one has the impression, at least from the chain of thought, that it is doing quite a lot of brute force search, and eventually it sort of just hits something that works and completes the proof. Sometimes they have clever ideas. This often happens, actually. You think, wow, that was impressive. And then on closer inspection, you discover that the idea that they had wasn't really their idea. It was just following a very similar pattern to a proof that's in the literature already. So they do have the advantage of huge knowledge of the mathematical literature. But that makes it rather difficult to assess whether they've done something very original or whether they're just using what for them is a standard technique, because they have this such wide knowledge of the literature. Of course, that doesn't mean, it's still extremely useful to have a research partner with this very wide knowledge. But as I say, it's difficult to evaluate. And yes, no, I've already said that we can't sort of easily work out what its proof searching method is. Is it doing a lot of brute force search and just telling you about the bits that worked, or is it more systematic? So okay, I think I've covered some of these points, but so one of the things that is unsatisfactory about it is that for our proofs, sometimes we want to guarantee that a result is correct, and that's a very important function that a proof plays, but actually we also want to develop mathematical understanding from a proof, and one of the ways that we can develop mathematical understanding is to have some idea of how the proof was discovered. When I read a paper, I want to know what was going on in that mathematician's head that enabled them to find this proof that I can learn from, so that in the future I would be able to find a proof like that. That's the sort of interrogation one wants to do. I don't want to say that LLMs are unique in having this difficulty, because if you look at the mathematical literature, it's also like that. This is a very important point. The mathematical literature is written in such a way that it just tells you the answer, and or a lot of it is anyway, or perhaps the majority of it is written, it just tells you the answer. It doesn't tell you how the author discovered the answer, and to get some insight into how the author discovered the answer, it can be a very difficult thing. It can be almost as hard as solving the problem in the first place. And actually, I think that's important because I think LLMs are trained on that sort of literature. So I think part of the reason that they have this style that they just tell you the answer is that that's what mathematics looks like to them, because they get the maths literature, but they don't get all those conversations with other maths teachers and colleagues and things like that that human mathematicians learn from. So that's actually very relevant to what I'm going to come to in a minute. But so one other point that I've not covered. So I've talked about evaluation of AI mathematicians and how original they are, how we can tell how original they are. But another point is that at least it seems as though LLMs are doing mathematics in a rather less efficient way than human mathematicians, using much more processing power than a human mathematician, or taking many more proof discovery steps, so to speak, doing big brute force searches where a human would prune the search tree far more ruthlessly. And if we could understand the human mathematical proof searching process better, that raises the hope that we could teach LLMs to find proofs much more efficiently, which would have all sorts of benefits. So one obvious benefit it would be that they would work faster, they would be able to find more difficult proofs, and there's also an environmental benefit that if they're doing a lot less processing, then they're using less water, emitting less CO2 and things like that. So I think there's a potential reward to understanding better how LLMs do mathematics. So I just want to talk very briefly about work that I'm doing in Cambridge with a group that I had funding for from an organization called the Astera Institute. So I have a group that works in automatic theorem proving. And when we started out, it was just before ChatGPT appeared on the scene. So it was a rather strange time to start. And our hope was to do something like this. We would really understand as well as possible how humans find proofs, and then try to automate that process. And so that we were avoiding the use of AI, and we were also avoiding as much as possible any use of brute force search. We really wanted, because brute force search gives you a sort of temporary advantage, but it doesn't scale very well. If you have to do several steps in a proof and each one has a large search, then you get a combinatorial explosion very quickly. So we were really trying to understand, and understand by which I mean reduce the process of searching for proofs to a sequence of what we call proof discovery moves. I haven't really got time to say exactly what I mean by that. I'll give you some little idea in a minute. At the moment we're engaged in, we've got another grant which is funding us to build a platform which will implement what we call proof discovery moves. So I'll show you I can't give you a demonstration, but I can show you what the sort of platform looks like at a particular moment in time. And the hope is that when we understand these moves, then the user of the platform will not have to type in anything when they're finding a proof. They'll just be able to sort of point and click and select a bit of text and say, oh, this is what I want to do to that, and so on. And for us, that's a sign that a proof is properly motivated, because if you can just reduce it to standard proof discovery moves in some way, then you've got, at the end of it, you've got an object where it's very transparent. You can see exactly how the proof was generated. And so we want to use the platform to produce a database of completely transparent proofs, and then use those transparent proofs to train LLMs, so that they can look at them, and instead of just looking at the sort of typical mathematical literature, they can look at data that tells you how the proofs were discovered in a human sort of way, and hopefully much more efficient way. One other thing that the people in the group are doing is creating new tactics for Lean. Lean is very much focused at the moment on verification of proofs, checking whether proofs are correct. But it doesn't support very well thinking as you formalize. You normally have to sort of first think, find the proof, then formalize it. And we're trying to produce tactics where you can do it all at once. I'm out of time, so I'm going to just show you quickly roughly what one page of the platform looks like. Don't worry about the details here, but we've got a collection of variables, a collection of hypotheses, and this is the current goal, which has changed from the original goal. Here there's a selected statement, K is compact, and up here there's some suggestions about what you could do. And one of them is unfold the definition. So you might say, one of the things you might do in the middle of a proof, you've got a hypothesis that K is compact, and you might say, what does that mean? So you click on unfold the definition, and then you'll get a new hypothesis that will say in much more detail what it means to say that K is compact. Don't worry if you don't know what it means to say that K is compact. That's not the point here. The point is that that's just one of the standard things that a human mathematician would do in the middle of a proof. So that's just to prove that we do have a prototype. It's still a little bit primitive, but it's developing all the time. So I hope that in not too long, there'll be something that you can play with. It's on the web, and I hope that in not too long we'll be able to go public with it, and you'll be able to play with this platform. Okay, thank you very much. I'd better stop there.